This is lab 4 bar magnets by Manveer Singh. So introduction, the purpose of this lab is to measure the distance dependent magnetic field of a small bar magnet and is to compare observed versus predicted distances of on-axis and off-axis magnetic fields. And then using GlowScript, which is our computational model, I created a computational model to determine the theoretical magnetic field. In a brief preview of our results, we have an n value of negative 2.626, magnetic dipole moment of 3.8837, and then our system is the bar magnet, and the surroundings is everything else, which is the lab room. So some fundamental principles in this lab were the Biot-Savart law, where this gives the magnetic field, and then we of like a normal, in a sense of like a point charge magnet. And then over here we get it of a magnetic field of like a dipole, where that's given over here. And then we also use a distance dependence formula, which is here, and the linearized form is given here. So experimental procedure. So the first step is to orient the phone to make the magnometer on the magnometer app orthogonal to the Earth's magnetic field, which you can see over here. And then 2 is to find the location of the magnometer chip on the phone, which you do here. And then 3 would be you would measure the distance between the magnometer and the bar magnet for on and off axis, which you can see we do that here. And over here is just a photo of us conducting that. So our data analysis for on axis, we had to input our data into the spreadsheet. So over here are our distances given, and over here are the averages. And you can see that this chart over here plotted the averages using a line of best fit, which is given right here. And this is what was actually used in the values that I provided earlier. And again, these just calculated the average distances and the average magnetic fields, linearized them, and then made a line of best fit for a field versus distance. So our calculations, the magnetic field of bar is given by this equation, where over here we were given the values for R and N, so we can plug that in and get the value of that. And then over here, N was again the slope of this graph over here, which is this negative 2.676. And then over here, the natural log of K, that would be the y-intercept again, which is negative 13.99. And then if you linearize that, you get the K value. And then our dipole moment was 3.8837. So data analysis off axis. So this again was in the spreadsheet, and this was also calculated similarly to the on axis, in which we just have 2 separate perpendicular distances now that we have to account for. So again, this was like the on axis and this was the off axis, and over here we are giving the d perps over here, and then we are also given like the averages as well. So our GlowScript computational model, over here is where I inputted the initial conditions, which would be like the position vector. This is the K constant. This is like the radius of like the bar magnet, etc. So over here we have some equations that we inputted for like finding the position vector, and then the magnetic field, and then the perpendicular distance and everything. All of this is just sort of our initial conditions. And over here you can kind of see our the different vectors, where over here you have like the diagonal at B at a 45 degrees, and then over here you have like the different perpendicular and on axis. So similarities and differences. So observed results on our off-axis B field, that's given right here, and our net was 5.6 times 10 to the negative fifth. And our computational results, that's given here, and our net was 3.49 times 10 to the negative fifth. These are somewhat similar, but yet they are still a bit different, and we will consider that through our error. So errors and assumptions, we assume that the bar magnet acts as a magnetic dipole, and that the magnetic field falls off as distance increases. And some potential sources of errors was that like there was like nearby laptops and phones that may have impacted the magnometer data collection, and the exact location of the magnometer was not found precisely. So statements observed, which of the statements describe what you observed? It would be this statement and this one, which is when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction, which is like, you can see why our graph sort of like went down like this. And then the magnometer, as it moves closer to the magnet, the measured x component of the magnetic field increases, again, which is why the graph is like this. So what ifs? What if we didn't orient it to compensate for magnetic north and just laid out the meter stick at some intermediate angle How would our results change? Earth's magnetic field would interfere with the bar magnet's magnetic field, which would skew our results. And then what if you were to stick two identical magnets together end to end and run the experiment again? The magnetic field's magnitude in this case would then double, but the direction of it would stay the same. So that in conclusion, we learned about bar magnets and how to calculate the magnetic dipole moment. We saw how to compare experimental data to computational, and we saw how magnetic fields work and calculations behind them. Thank you.